Hi everyone, I'm very excited to present here for the first time at Conflang, and I'll be talking about typing in configuration languages, and more specifically in Nickel. Nickel is a language we are developing at Tweag. It's designed to be both a general purpose configuration language, but also to work with Nix. Nix is a package manager and uses a specific language to describe software packages. And talking about typing is talking about static typing versus dynamic typing. A program is usually a set of transformations that you apply to some data. But it turns out some operations or some transformation only apply to specific data. For example, addition only applies to numbers and not to number and strings. And typing try to solve this problem of can we check somehow in advance if some data will satisfy the condition required by some operation. And unfortunately, in Turing-complete languages, Rice's theorem tells us that any non-trivial such property cannot be decided. No program exists that can say in advance if some expressions will eventually evaluate to a number. So faced with this problem, static typing chooses to approximate the property we want by a more restricted decidable property. So in exchange, we will have probably to help a bit the type checker by adding a notation, and also it will necessarily reject valid program or program that runs without problem. Dynamic typing, on the other hand, embraces the fact that you cannot decide those properties in advance and just let the user write whatever they want and check at runtime when applying these operations that the conditions are satisfied. And this incompleteness of static type system manifests in concrete way. The standard example is if you have an if then else. Usually a static type system wants all the types of both branch to be the same or to be compatible. But actually, if you write an if then else and that the condition is always true, then in this example, x will always be 0. So at runtime, it will always be a number, and this is fine, but this program would be rejected by most type system out there. On the other hand, dynamic type system just wait to actually have the value of x, and so they can check that x is a number and that everything is fine. So they are complete. That is, you can write any program that won't try to add a number and a strings at runtime, and it will be accepted. But somehow it's complete in a void way. It just waits for the actual addition to check for the condition. So it's too late. First, it's non-exhaustive, so static type system ensures safety properties for all possible code paths. But more importantly, it's non-local. That is, if you take the following example, we have a flatten function that takes list of list and return just a list without the inner list, and it's applied and throw to a value that is of the wrong shape. The last element is a number, it's 4, and it should be a list. And if you do this in a dynamically typed language, you won't get an error at line 4 when the ill-typed value is introduced, but when it's eventually used with the built-in operators, which is concatenation, line 2, inside the flatten function. But the flatten function is totally fine, it's actually well-typed, and we get an error inside the body of flatten, which is really bad from the user. And if we try to abstract a bit away of this is a problem of boundaries. So flatten defines some boundaries, and flatten is actually safe. But the problem is that the coder can introduce arguments of the wrong shape, and it won't get caught as a boundary, that is at the function call, but it will get caught only inside the function code when it will be used. And this is something that is not really working out. And to extend this notion of safe boundaries, we can talk about the parse don't-validate approach, which is it's an approach in a statically typed language that push to somehow extend those safe boundaries to the whole program and not just to functions. And that says that every transformation you apply inside your program should work on type data that ensures that the invariants hold. For example, if you are handling a URL, then you shouldn't represent them as strings inside your program, but you should parse them to a specific type representation, then apply all your transformation inside the program, and then only at the end you can serialize them back to strings for other programs to consume. It looks like static typing is winning here, because first it offers you static guarantees for all possible code paths, and second, it gives you early error reporting. However, I want to underline that configuration languages lie in a specific location in the design space of a programming language. And the first specificity is one of lifecycle. So if you imagine a standard application, say a web service, it's going to be compiled once and then maybe run for hours, days, or months, interacting with a lot of external data, client requests, databases, a file system maybe. On the other hand, a configuration program is usually a terminating program that runs on fixed inputs. So it may be parameterized by some data, but once it started to run, it doesn't communicate with the external world. And actually, most of configuration language are pure. And this makes for a more limited or blurry compile time versus runtime dichotomy. In particular, you are not going to, as with the burp service, wait for 1 month to trigger some obscure code path and get an error. Usually, either a configuration program succeeds or you get feedback immediately on what is the problem. Same as with one-liner or scripts. The second point is that of the separation between computations and data. So computations are what makes those language appealing as compared to, say, basic JSON and YAML. It allows you to generate more data from existing data, to describe dependencies or transformation between data. And those computations are expected to stay in the built-in and in libraries, and basically those are the functions. On the other hand, you are going to write a lot of configuration code, which is 99% data. Of course, you are going to use sometimes some of those computations, but most of it is data. And in this setting, typing is a bit less, say, appealing, because it's about transformations, right? It's about having the right shape of data for the argument of operations. And so let's see how this translates in the wild and how it affects the approach of various configuration language with respect to typing. So we can start with the next language, the current one, which will be somehow baseline, and which is a very simple language. It's JSON plus higher order functions, basically, and it's used to describe software packages. So it's a simple, functional, and pure language. It's dynamically typed and Turing complete. And we'll see that the issue I described before about early and later reporting are not just theoretical, they are practical. And for example, this is an example by Gabriela Gonzalez, the author of Dhall, about dynamic error reporting. And this is a simple program that try to set up a list of options. And you see line 6 that it uses a little helper, enable define line 1, which is a function, applies to a string, and that should return a string that will go in the option list. However, if you try to run this program, you will get these strange errors located somewhere in some internal Unix code about functions not supported for make value string default. So what the hell is happening is that in Unix, the space is used both to separate list elements and also function application. And so when you think that you wrote a list element which is enable apply to fallback, actually you wrote two different list elements. One is enable, a function, and the other is fallback. So at some point, Nix finds a function inside the list of options, which is expected to be a string, and everything failed. But it happens way late in the pipeline of the program execution. A second example is one that I experienced myself. I had to migrate my Nix configuration to something else called Flakes, and I had to add line 1 and line 4 this module path argument. So this is a function, and line 1 you define somehow named arguments, and then from line 3 this is a definition of this function. And when I tried to rebuild my system, I got this very strange error about infinite recursion encountered at some place. And I didn't even use explicitly or obviously recursion, so I didn't know what was happening. But it's linked to the way Nix is building the configuration. But it's kind of beside the, it's not really the important point. The important point is that I made a silly typo, putting a S at the end of module path, what it was actually modules with the S and path. And this kind of errors should be, easy, or at least it should be doable to catch them beforehand with some form of typing. This is not really nice to get this infinite recursion because I misnamed a function argument. So Dhall is saying, okay, let's add just static typing to such configuration language. So it's not exactly Nix, but this is the same spirit. JSON data structures plus higher order functions plus static typing. So it's not especially targeted at Nix, although you can use it for Nix. It's also for cloud like Kubernetes in particular. And not only it is statically tied, but it's also non-Turing complete, meaning that all programs are certified to terminate. And it has a powerful type system, not just like the standard package, but actually a form of dependent types. And so this is just a simple example to give you a taste of Dhall. So we define a function that takes a number and compute the age of someone from its birth year. And then we just generate standard JSON structure, which evaluates to what you would expect. However, types in Dhall can become a bit verbose. So this is an example taken in the wild, someone code base, and which defines the usual filter map higher order function. And so you see at line 2 that there is type signature. This one is pretty standard. It's a generic function of two types that takes then a function and the list. But line 3, you see that when you declare the arguments, you have to also declare the type as argument. And line 5, when you apply a fold, you also have to pass so you have to tell fold to which generic type you are applying this fold. And to conclude also, you have to declare the type of the argument of the function you are folding over the list. And to wrap up, so Dhall brings safety and structure, basically a type system over basic Nix, and it solves a lot of error reporting problem. It's a particular expressive type system, and it enforces termination. However, because of the power of the type system, type inference is limited. In particular, you have to annotate functions arguments, and you have to do type application and abstraction, that is things linked to polymorphism or generic code, we could say, explicitly. The two last points are not necessarily with respect to Dhall especially, but usually in generally with statically typed language, interacting with untyped or unstructured code or data can be a bit annoying. So in particular, recursive structures need to be encoded in Dhall. Union also need to be tagged, which is not a blocker, but not always perfect. And also that you may want to do some things a bit more involved than just checking that things are number or have the right structures. For example, you can want to check that an integer is in the right interval, or is valid part number, or that the string is valid URL. And this starts to be really, really hard to do for any static type system. So in Nickel, what we did was to add something for this validation, missing validation, which is contracts. And we do have static typing, but it's optional typing. I will come back to that in a few slides. And so the first, it initially was created as a response to the shortcomings of the Nix language, but it's also a standalone language that is designed to do a general configuration, same as Dhall. So it's functional, pure, and Turing complete. It mixes both static and dynamic typing and those contracts. And it has a merge system that I won't have much time to expand on. So if we go back to our flatten example, in Nickel we can add a contract annotation. So in line 3 you can see that I have added a list of list num annotation, but with a pipe. And as opposed to the colon, it means that this type is going to be checked at runtime. This is a contract. And as opposed to our first example where we had the error inside flatten, here we can see that the error is actually located at the right place and says what we need to know, that the problem is that the inner type of the list was expected to be a list of number, and I got 4. So this is a contract for you. This is similar to types. You can even use the same syntax, but the difference is the time when it is checked, and it's checked at runtime, exactly as dynamic type. So those are like assertion, but succinct and composable. By composable, I mean the same as for types. You can use type constructors, list, the arrow to compose them. And importantly, of course, you could use like standard assertions, but the error message would be much more limited. With built-in error reporting, you have access to a lot more information in the interpreter to be able to give nice error message. So those, one important point that annotation are not just for static typing, right? This is some kind of cultural thing that dynamically typed language should only check arguments of operation implicitly, but there is no reason for that. And you could add dynamic type annotation to any dynamically typed language out there, and it will already make things better to allow to insert explicit checkpoints where some data should be satisfying some property. So this is one ingredient of contracts, somehow being able to explicitly add annotation. The other difference with vanilla, let's say dynamic typing, is that contracts accommodate for function. And so what is the contract for a function from numbers to numbers? Well, I cannot really do many things with function. It's a computation, it's inert, waiting for a value. But what I can do is to wait to, as custom in dynamic type checking, and wrap f with a function that will check for each call that the argument is of the right type, that is that x is a number holds as a precondition, and that f applied to this argument holds as a post condition. And so you may have see this kind of technique in, for example, PHP, which has type hints now. But in PHP, it's not. You cannot write higher, for example, higher order types or things like that. So it's from a partial implementation. And Python and Ruby have just the syntax, but currently doesn't do anything dynamically. So those contracts are interesting, but for flatten example, actually in Nickel we just type it. It was an illustration, but it's a bad example for contracts, because here static typing is perfectly adapted. You will check the body of the function and any call to fold or flatten. And actually, since you can write untyped code in Nickel, the interpreter inserts automatically a contract to protect flatten, because even if flatten is typed, maybe somebody else can still call flatten with the wrong argument we saw before. And so the interpreter automatically inserts an appropriate contract to protect flatten. It's called sound gradual typing. So given this, we could say, okay, why do we need these gradual typing things? Contracts are nice, but they are not incompatible with static typing, actually. We could have a statically typed language with contract on top of it, just for advanced validation. However, it's a bit of resaying what I said about configuration code versus computation, is that configuration code is mostly data that you don't really transform, that are consumed or transformed outside of the boundaries of the program. And they need validation anyway. And I mean, if you are checking that something is a valid port number, it doesn't really add anything that the type checker checked before that it is a number. And so I would say it's more of a joke than an actual motto, but validate, don't parse in this situation. So this is an example in Nickel when you can define contracts. Actually, they are just some form of validation function, line 1 and 2 for port and an URL that check that some value is a valid port number or a valid URL. And then you can use it to build a new contract, which will be the schema of our configuration, that says that you should have a field name ports, which is a list of ports, and a field name domains, which is a list of URL. And with this, you can check already interesting property, and you use more or less the same kind of annotation as with types. Once again, the difference is when and how this is checked. One bonus with contracts is that you can implement some form of pre and post condition of function. So for example, I can annotate domain of and say that it should take URL and it should return URL, and it will add checks to every call of to domain. Second bonus is that Nickel aims at interacting with Nix, and we can imagine at some points that we will need to accommodate or being able to import or to interact with existing Nix code. And as any dynamically typed language, existing Nix code makes use of idioms that are really hard to type. So there is a call package, for example, design pattern that I won't describe here, but it implies looking dynamically at the argument, name of the argument of a function. And a more mundane example is this inquiry function that take a function, a list of arguments, and apply f to each of the elements, which can be typed in some type system, but not so easy to do. So being gradually typed allows for interacting with Nix as an untyped language. So to sum up, in Nickel you have somehow types à la carte, meaning that you can choose between dynamic and static typing. This allows for embedding untyped code. One important point is that you have built-in features to represent schema with built-in error reporting as contracts. And also a point that I want to make is that dynamic type errors can be relevant if you add the right ingredients, and the right ingredients are, I think, annotations and this kind of built-in error reporting that comes with contracts. One of the possible shortcomings is what I call the untyped temptation. With any gradually typed language, well, you cannot prevent someone from writing totally untyped code. I think that it can be mitigated by with the community and the existing library code and documentation to make very clear and sure that there is a culture of typing anything that is not configuration code, but it's still a pitfall. The second point is that contracts do have a runtime cost, and most of the validation contracts are fine because you want to validate your data anyway, but some hidden costs are the cost of the contracts inserted automatically. So it's documented in the literature. It may be mitigated. Performance is not as important or not the same in configuration language as in the general language, but still this is some challenge to keep our eyes on. Then I want to end with Q. Q is kind of an outsider in this setting of static typing, dynamic typing. So it's a much more restricted language. It's based on unification that you could think of as some very simple form of substitution, and it is very computationally restricted. You don't have a notion of function and even less of higher order function. And in exchange, everything is a type in Q somehow. So you can see values just as types that are so restricted that they are only inhabited by one value. And then constraints correspond to more general types. And so you can refine your constraints until a value. And all these types and values live in what we call a lattice, which is a pedantic word to say that you can always take the intersection or the union, basically, of your schema or data. And this will be well defined. So here, a little example in Q, you can define the schema on top and say that it must have a field name that is a string. You can add some kind of integers constraint also. And then you see that human is defined to be true. So already in the schema, we can have a very precise value, that only one value is possible. And then Viola will be, in practice, your configuration. But in Q, it's also a type. It's just a very restricted type. And line 7, you enforce that Viola abides by the schema defined line 1. Still, even if Q doesn't have function, you always need sometimes to apply some treatment to your data. So it has comprehensions, a lot of built-in functions like this list sort strings line 4. But still, people need to resort to function. And you can encode some functions in Q using merging, actually. But it's not very ergonomic. There have been some discussions about adding a better syntax for that. Maybe that would help. But I want to say that if you compare to the example on the right that does the same thing, if you start to have function, even if in a restricted way, then I guess this functional syntax is more adapted or more readable than this kind of encodings on the left. And to sum up, so Q takes a very different stand with respect to typing and even computation. So everything is more restricted. It's closely following the philosophy that somehow configuration is not the same as full-fledged code. And it brings a lot of nice behaviors in this language. So you can do static analysis, you can do trimming, which removes duplicated constraints, querying that gives you an example of a value that satisfies a type, and so on. And so also it's interesting in its simplicity because of the limited computation and override, which are the fact of taking a computation and redefining some part of it, which makes it more readable, for example, for people that are not accustomed to general purpose programming. What is both a perk and a shortcoming is those limited computation. So as long as everything you need to do fit in the framework, this is great. But sometimes, and I think about the build system in particular in Nix, or even in Bazel with the language they use, Carlark, you need to do some things dynamically that are not trivial, like simple parsing or building a dependency graph, basically. And in this case, the limited computation of Q can become, quite complex. And to conclude, I want to make the key observations that first, configuration languages are peculiar in the design space of programming languages. And this means that we can try different approaches, in particular with respect to typing. Despite this, traditional dynamic typing just doesn't scale, as experience shows us with Nix, but also with other untyped or dynamically typed configuration programming language. There's no silver bullet. There are different trade-offs, which are all valid, at least the ones I presented in this talk. So there's Dhall that says just use static typing, and I want to cite Grace, which is a new language by the same creator with better type inference and less expressive type system, which is an interesting trade-off. Then there's Nickel that says, let's use typing, but we also want something more powerful to check the validity of configuration, to do validation. So we have this contract, but then with contract, statically typing configuration code doesn't really make sense anymore. So we relax the typing to be gradual and allows both for dynamic and static typing. Then there's Q that is quite different and takes the position that configuration shouldn't be too powerful, either computationally or also with respect to overrides. So this ability to take a configuration and change some values. And so there's this language where everything is a type and live in a lattice. And I must say, I'm just really excited to see how those languages will evolve and if there's some approach that stand out in the future once we have more experience with configuration. Thanks.